Hi, I'm Ben-Yaakov. This presentation is entitled Static Reverse Current of Schottky diode. In this presentation, I'm going to discuss the issue of reverse current in Schottky diodes, and then to give some examples of when this reverse current is really harmful. Now, silicon diodes, or the regular diode, I'd say, are built around a p-n junction of a semiconductor material. And then we have the Schottky diode, which is built around a junction which is between metal and a semiconductor. And this semiconductor could be silicon-based or silicon carbide. I'm going to discuss in this presentation the silicon case, that is a junction between a metal and silicon case. And this is the so-called Schottky diode. The silicon carbide is also a Schottky diode, but then the semiconductor is silicon carbide. Now, when we talk about diode, what we envision is a device that will pass current in one direction and not in the other direction. In reality, all diode, all practical physical diode, will pass current in the reverse direction. Well, it could be of different magnitude. Some will pass a higher current, some lower current, but there's always some leakage current across the junction when it is reverse biased. Now, Schottky diodes are favored because they have a low forward voltage drop, so the losses during forward conduction are lower. They are fast switching devices because there is no stored charge in the junction. However, there is a junction capacitance that to some extent behaves like a stored charge, that is a reverse recovery of a diode, but the total charge is usually smaller. Now, the question that I'm posing here is, what is the magnitude of the reverse current in Schottky diode? Now, Schottky diodes are considered to have a relatively high reverse current as compared to silicon diode. This is very well known. But the fact is that Schottky diodes of low reverse current are also commercially available. So what is the story behind it? How come we have diodes of high current, high reverse current, and diodes of low reverse current? And here I'm showing a comparison between a silicon diode, a p-n diode. I've chosen one with very low reverse current, and a common Schottky diode of, say, 1 amp in this case. Now, if you look at the reverse current magnitude in this case, where the scale here is in picoamp, and say at 10 volt, we have only 4 picoamp, while here at 10 volt, 25 degrees also, we have 0.1 milliamp. Well, it's a couple of order of magnitude larger. Again, I've chosen here a diode which has a low reverse current, but the point is that you cannot get such reverse current with a Schottky diode. If you compare two Schottky diodes, you find that some have a very high reverse current. For example, this one is a 3 milliamp reverse current at 10 volt, while this one has a reverse current of 15 nanoamp, same 25 degrees. Again, it's a very big difference, and both of these are Schottky diode. So what's the story about it? Well, it turns out that the reverse current is linked to the forward voltage during conduction. Now, a lower voltage drop in Schottky diode is achieved by lowering the potential barrier, and this increases the reverse current. So what it turns out, that the lower the forward voltage drop, if you design a diode for a lower voltage drop, then you end up with a diode that has a larger reverse current. So these two are linked. And this is why you can get a diode with a lower reverse current or a higher reverse current. But if you look carefully, you'll see that there is a linkage to the forward voltage. And here I'm giving two examples. Now, this diode is specified as a diode of a low forward voltage. Okay, and indeed, this is a 1 amp diode. Indeed, at 1 amp, 25 degrees, it is 0.3 volt. Very nice. However, the reverse current at 20 volt is 0.3 milliamp. That's quite a bit. If we compare it now to a diode which is specified as a low leakage current Schottky diode, then you see that indeed the reverse current is low, 20 nanoamp, but the forward voltage is high, well, almost twice that we had before. So again, there is a linkage between the two. There is no free lunch here, and it's a compromise, a trade-off, and one has to decide what is more important in a particular application. Now, is reverse current really harmful? Well, in some cases, in particular in standby mode, that you like to have as low power loss as possible, you might have quite a bit of power loss due to the reverse current, because the reverse current means that you have a voltage drop, reverse voltage on the diode, and then if the reverse current is high, then you may have a loss which is significant to the standby power loss. So this is one case that reverse current is really not good in this situation. But there are other situations. I'm bringing here two cases which are related to sensing, you might say. Okay, here I'm showing a case in which you have an OR arrangement between two power supplies, say two batteries feeding a load. Suppose the voltage V2 is higher than V1, then there is a conduction here. And now in many applications, you like to sense to see whether there is a voltage here, or there is a connection to a battery, say. And if you put here a voltage sensing device, which will have some internal resistance, which will usually be high, you will find that there is a voltage here, because there is the current, and then there is an error voltage here. It's supposed to be nothing, but it is not. You have the voltage imposed by the current, the reverse current here. Another case, which is really very popular, is that in many applications, many circuits, we put a clamp diode between a line, a sensitive line, to the power supply, to VCC, okay? And here I'm showing like an A to D, it could be part of a microprocessor, and then there's an amplifier, and in order to protect this point, which is sensitive, it could be damaged by spikes of high voltage, we normally put a diode between here and here. Now in this case, you have a reverse current here, which is of course corrupting the magnitude of the voltage here, which is very bad. In fact, I've seen many cases in which the diode was not picked up to be of a low reverse current, and indeed the error was very large. So what's the conclusion here? Schottky diode of low forward voltage have a high reverse current, that there is a linkage here. And this high reverse current can cause either power loss in the case that you're talking about situation that the total power loss is low, and sensing error that could be in many parts of a circuit. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.